the seminar. So we are very pleased today to have here as our guest Professor Jiancang Zhuang. Is associate professor at the Institute of Statistical Mathematics in Tokyo, in Japan, and is working, is belonging to the Statistical Seismological Research Group, and indeed is working a lot on earthquakes and specifically on the well-known method ETAS that he's going to present today. And well, I think most of you know him or his work. So feel free to ask him questions. It's a good opportunity to have him here. And so don't be shy. And give you the floor. Thank you.
Okay, thank you for introducing me. Today my talk is on the epidemic aftershock sequence model, the ETAS model, basically on its history, application, and some extensions. So this is outline of the talk. The first part is on history, some history of the ETAS model, and then the ETAS model related to the Statistical declaration and reconstruction. The part 3 is on the extension of earthquakes. So some histories. So everyone knows about the empirical formulas in seismology. So one is the Gutenberg-Richter formula. It gives the relative frequency of earthquakes in a catalog, which is log linear formula. So in probability, it is an exponential distribution. The events above MC, say M, have a probability density of exponential distribution. So if we plot it in logarithm, so this the frequency and the magnitude in logarithm is related to energy of moment. So it's a linear formula. So this is one. The other famous one is the Marinwood formula. So this formula is much older than the Gutenberg-Richter magnitude frequency formula. So it was developed by Omari in 1898. At that time, we have no concept about magnitude, earthquake magnitude yet. So Omari counted the number of field earthquakes after the Novi earthquake, and then he has such kind of inverse power law. At that time, he used P equals 1. So later on, Wutsu in 1950s, he found this aftershock decay maybe sometime often slightly faster. So this P is changed. This P is added to the formula. So this is an example of the Kobe earthquake in 1995. We can see how the aftershock frequency decays. It's according to the Omari law. So, but this is not the whole story. Also found not the main shock. The big aftershock itself also triggers its own aftershocks. So he proposed a multiple Omari formula by adding another inverse power decay terms to the aftershock frequency. So Olga, if we look at to model a wide area of seismicity, so it seems become a bit tricky. So if we look at this is seismicity in the central west Honshu Island of Japan. So we can have some cluster which is only spatial concentration and earthquake occurring continuously around the same location. And of course, we have other aftershocks sequence like those ones. This is the 1995 Kobe earthquake. So it's a temporal cluster, so which so-called earthquake sequence. So based on the Omri formula and the Hawkes process, Ogata thinks not only the big aftershock, each aftershock produces its own aftershock. So in this way, we needn't distinguish which is main shock or big aftershock, which can trigger aftershocks. So each earthquake itself can trigger earthquakes. So what he write, in 1988, he proposed the temporal ETAS model. 10 years after, he again proposed the space-time form of the ETAS model. So this is the space-time form. In this model, we have background seismicity. The background seismicity is assumed to be constant in time, but in space, it's inhomogeneous. And also, once we have an earthquake at Ti, so it will excite a kind of non-Poisson process with such a rate in space and time, depending on the magnitude. So this is one angle to view this formula. Another meaning of this formula is if we stand up at a location x, y, and a time t, the seismicity rate consists of several parts. One is the background part. The other part is the triggering effect from all of the past events. And this kind of triggering effect depends on the time difference and distance to the past event. Of course, also the magnitude of past event. So this function kappa of m is the productivity of the events with magnitude m. So it is the average number of trigger events. So the number of trigger events in this formula in the ETAS model is in fact a Poisson random variable with a mean value kappa of m. So this formula is based on the Shimazaki formula in 1990s. In fact, Ogata used this formula in 1988, even more earlier than the Yamanaka and Shimazaki. So the second formula, this one, G of T, is the Omri formula. So it's the probability density format of the Omri formula, which is also called the Omri-Woods formula. The third one is the spatial response to aftershocks. So it takes inverse power law form with a scaling factor of the correlated with the positively correlated with the magnitude, this positive exponential law. So this is the formula by myself and Ogata in in 2005 and 2006, after we compare several candidate format. So, and then the second part, I will say something about the epidemic-type aftershock sequence model and extensions. So this is the original ETAS model. So related to the ETAS model is the big classroom. We can say the event J is produced from the background. It is in fact the relative, the ratio of background in the total seismicity, in the seismicity rate. So also the probability J is triggered by I, we can estimate it by the triggering effect to J by I divided by the seismicity rate at the occurrence time and location of J. So this is in fact, oh, sorry, how can we go back? Okay, so in fact, it's just divided the whole formula by lambda from both sides. Then we will have this one. So this means each event can be sliced into background part, into the part triggered by event I. So of course we can generate something like the background catalog, or to find the family tree in the catalog. So the algorithm is quite simple. For each event J, we generate a uniform random number within 0 and 1. So if this uj less than the background probability, then the event J is background. Otherwise, we just found at what stage this term began to greater than this random number, and then we set K to be the mother event of event J. And also, the parameter in the model is estimated by an iterative algorithm. This is because mu is a non-parametric form. We have to estimate by some non-parametric estimate, and also the parameters inside the model. We have to we can estimate through MLE, maximum likelihood estimate. This is when this background is known, but it's unknown. So because it's unknown, then we can carry out the stochastic classroom procedure to calculate the background probability for each event J and the probability event J triggered by I. And after that, we can smooth the background by this kind of, this is the kernel function here. And then each kernel we weighted by background probability, and the estimate is then the background probability, the background rate, and we can make a loop of those steps until the results get converging. So this is one of the examples for the Central West Honshu Island data. This is a histogram of the aftershock probability. It's 1 minus 5J. It is this part means the background. This part means aftershocks. So we can see most of events here are as the background of aftershocks. So quite a few of them lies in between. So now we to see the second part. I think I always make mistake with number about the extension of the ETAS model. So because ETAS model is quite powerful in analysis in the analysis of seismicity, so a lot of researchers trying to make extension of this model, especially the first thing is the depth. So we also considered this problem. So first one is to think about the depth, how we can put the depth inside. So this extension is done by, implemented by Yifeng Guo. He was a PhD student in Peking University and now a postdoc in my research group. And to put the depth in ETAS model is not so easy. This is because the depth is different from two horizontal direction. Aftershocks can go any direction on the surface freely, but to depth, because when it gets deeper, the static stress increases rapidly, and aftershocks cannot go infinitely deep. So this is one reason, physical reason. Another reason is the mathematical, numerical reason. If we put the z inside this function f directly, something like z minus zi, so we have the trouble because we have the limitation of surface for different depths. The normalizing constant for the PDF is different. We have to make such kind of normalization for each event. So considering those two difficult reasons, what we do is we add a separate depth component in the ETAS model. So this distribution is better distribution. So we assume the maximum depth, capitalized Z is the maximum depth, and the depth divided by the maximum depth is then we normalize the depth from 0 to 1. After this normalized depths have a distribution of beta distribution. So Zi is the depth of the mother events. So the mother events location determines the shape of the beta distribution. So this is different shapes of the beta distribution. So this part, if we mark where the mother event's location, it is the location of the mode around the peaks of the density. So this is the new ETAS model with depth. So the first experiment of this model is applied to Southern California earthquake data, and by comparing the likelihood, the ETAS model is much higher. The 3D ETAS model is much higher than the 2D ETAS model. We have to assume the depth distribution for the 2D ETAS model because 2D ETAS model has no depth information. So this is reconstruction results. So it is a method we plot after we separate the family trees in the catalog. Then we take out each pair and calculate the depth difference. Find the depth distribution for mother events at different depths. This is the depth of the mother event, and this is the depth for the corresponding for the aftershocks with corresponding mass events. So we can see this is when mass events is depth of 5, the aftershock distributed like that. The curve is theoretical curve from data fitting, and those cross and circles the empirical functions we estimate after we separate the earthquake in the into different families after by applying the Stochastic declaration method. So the second example extension is about the finite source ETAS model. So if we look at the ETAS model, the spatial response is isotropic, but the aftershock distribution always is anisotropic. So this is aftershock for the Tohoku earthquake in 2011. This is the aftershock distribution in 2010, the Christchurch earthquake. This is the main earthquake, which is called Barfield earthquake. So we can see use isotropic may not proper to describe the distribution for aftershocks. So Ogata used this form by adding a kind of something like a covariate for use bivariate Gaussian distribution, bivariate kernel with some correlation in between to model the aftershock distribution. So this is one way, because in this way he introduced 3 parameters for each aftershocks, for each earthquake aftershock sequence, for each sequence, 3 parameters are introduced. So how he estimates those 3 parameters? He first found the cluster by some kind of traditional window-based declaration method, and then calculate those 3 parameters by something like by data fitting. After data fitting, he fixed those parameters for the big earthquakes and then fit the ETAS model. So which makes the ETAS model is very difficult to calculate. So another one is done by Bach and Hans. What they think instead, when we calculate the distance between the main shock and aftershocks, it's not direct the distance. They use the distance to the fault trace instead. So this is one example for the California earthquake. So for California is very nice. This is because most of the faults there are something like a vertical fault. The trouble is if we have a deep angle, and how we can calculate the distance. So in the finite source ETAS model, what we think is the response should be always isotropic, and the source is not a point source anymore. So this is different from the previous study. The previous study is a point source. All earthquake, big or small, it is just a point at the epicenter location. So, and the response of aftershocks in space is anisotropic. Then we have the anisotropic aftershock distribution. But another idea is, if we do not regard the focal source of the main shock is a point, but source with extension in space, and each part of the earthquake source produces its own aftershocks, which have isotropic response, and then the overall aftershock distribution and is then anisotropic. So this is the new ETAS model. So for this model, we are still working with starting from the 2D epicentral ETAS model, and we have the same formula, but the only thing is changing is this part about the response. First, we classify earthquakes into two classes. One is a kind of point source, the small earthquakes, we still regard them as a point. But for big earthquakes, we can regard them as a finite source. So the SI is the area of the source of earthquake I. So this tau here is the productivity density along the fault. So each small part of the earthquake source produces its own aftershocks, have spatial response of this form. So this part here is for normalization. So this function is always a probability density. With this function in probability density, we can always say this part is the productivity function. So in this new ETAS model, we introduced one new parameter here, but we also introduced a kind of a new non-parametric form about the productivity density for each finite source earthquake. So in calculation, we did some discretization about by divide the finite source in many grades. So how to determine the finite source, the size? So what we do is we make a very large reading, which include all of the whole aftershock load, much bigger than that. After we some calculation, it's the boundary, the productivity becomes 0. So this is the discrete form for the response for when calculate the aftershock response for finite source earthquake. And how to estimate this part? So when those functions are known, we can estimate the parameter from MLE. And then we carry out the stochastic classroom procedure. We have background, we have J triggered by I, but we can also take one term from this summation again, and then we can calculate the event J triggered by the case patch of I. So this is this one. We can use this probability as weight to reconstruct the productivity density function tau here. So now, how to do that? We do smoothing part. The background smoothing is the one we talked before. But for patch productivity, so this part, the red part here, is the event triggered by patch I, by patch K here. And if we sum up all of the events J, so that's the number of events triggered by the patch K. So, and this part is Gaussian kernel function. It's just for smoothing to make the neighboring cells, neighboring patches have similar productivity density. And then we can make a kind of iterative algorithm to get the parameters and the background and the productivity, all the function converging. Okay, the third extension is related to the focal mechanism. This is work done by my PhD student, Eli Maita, and so the first thing to put the focal mechanism in the ETAS model, the first thing is we need a kind of good expression for the distribution of focal mechanism. So the focal mechanism have many kind of forms, something like three angles: strike, sleep, deep, and reach, and also moment tensor. Here, what we use here is, okay, we take a reference focal mechanism. For example, we can use a strike sleep with kind of something like kind of a strike direction to the north as a reference focal mechanism. Once we fix the focal mechanism, and then we find a rotation pole, and then about the rotation pole, we can rotate the beach ball, and then with different angle, we have a new focal mechanism. So this is the way to, in this way, we separate the distribution for focal mechanism two components. One is the rotation angle, which is called, also we call Kagan angle, and another is a kind of rotation pole for 3D direction. So another question is, what's the uniform distribution for such kind of rotation in 3D space? Kagan have did a lot of research. In his book, I published in 2013, he summarized the uniform rotation for focal mechanisms. So if we rotate the focal mechanism from the reference to the given focal mechanism, we require, when we rotate, the fold plane rotated to the fold plane, and also the hanging wall and the bottom wall are also identical to each other. So this is something like no symmetry is considered. In this way, the rotation angle is from 0 to 180. So so someone may ask, why not the rotation angle to 360? So this is because for 360 we can just something like something like look at another direction, rotate to another direction. It's this is something like changes the rotation pole to the opposite direction, and then it's the rotation angle is 180 again. So DC2 symmetry is if the fold plane is known, but we do not mind the hanging wall or the upper wall, the hanging wall or the bottom wall. You can rotate the reference bottom wall to the hanging wall or the bottom wall of the target focal mechanism. And then this is the DC2 symmetry. So it is this red line here. So the number of 180 rotations reduced a lot. So what happens with the DC4? DC4 means you can rotate because in the focal mechanism there are two planes, two-fold plane. One is the real focal plane, another is the auxiliary one. So you can rotate the focal plane of the reference to either nodal planes. So, and also which side we don't mind. So in this way, the nodal planes, neither the nodal plane nor the sides are distinguishable. And then we have those kind of distribution looks like that. So the angle is 120. So maximum here is still here is 90 degree. So what we do is, okay, we use the very simple 2D ETAS model, separate the main shock and aftershocks to separate the parent and children events. And then for each trigonal pair, we weighted them by the by this probability, even J triggered by I, and then we calculate the histogram of the trigger of the rotation angles. So this is the shape of this one rotation. So this one is from 0 to 120 degrees. This is the uniform rotation obtained by Higgins. So we can see the focal mechanism of the mother events and the child events are correlated very much. So this is the ratio of those two densities, which is decays quickly. This is for the trigonal pairs. And then if we write the new ETAS model, it should be a form like that. So the distribution of the new focal mechanism is only related to the rotation angles between the child events and the mother events. The mother event here is used as a reference focal mechanism. So, and the form, this form, can be a kind of scaled by a double exponential function. And what happens with the background? So for background, what we do is, let's use the average focal mechanism at each location as the reference one. So to do that, we need to calculate the spatial average focal mechanism for the whole Japan. So the calculation method is the Kagan injection in 1994, and here is the average focal mechanism for all the seismicity and the background seismicity. And then for background seismicity, each event is just weighted by the background probability. For total seismicity, each event is weighted by the weight 1. And so this is the distribution of the rotation angles for the background seismicity. So the background is the blue curve. And we also plot the rotation angle between trigonal pair and uniform. So we can see the rotation angle is quite concentrated. For the trigonal pair, it's concentrated to the mother event. For the background, it's around the average focal mechanism with similar form. So this is a new ETAS model. We can put the background focal mechanism with phi0 is the average focal mechanism. It's location dependent on X and Y. And the distribution is with the rotation angles. So this is scaled. This is the uniform rotation scaled by a double exponential distribution. Because we require this to be probability density in fact, only one parameter are introduced here, and another parameter introduced here. Now, so this is the, so the summary, the summary for this one, the focal mechanism can be also included in the ETAS model, and the ETAS model and aftershock have similar focal mechanism to their main shocks. New ETAS model will input the data fitting and show correlation of the between focal correlation between focal mechanism. Oh, sorry for this one. And also stochastic reconstruction method help us to build a proper form of the ETAS model. And now I think the time, should I stop? Oh, I see. I quickly go through the results to the Italian catalog about the new model. So this is an Italian catalog, it's the ICD catalog, and compared by INGV. The catalog is from 2005 to 2017. I only consider the magnitude 2.8, 2.9. This is relatively complete in the catalog. So there are about 4,452 events. So we have 6 events greater than 5.5 during this period. We use those one as something like a kind of, oh, sorry. We use those one as finite source event. Now we apply the 3 models because I have no focal mechanism data. The focal mechanism ETAS model is not applied. So we have 2D ETAS model and 3D ETAS model and finite source ETAS model. So what happened to me is the difference value of the alpha value here. So for the finite source ETAS model, the alpha value is about 2. And for 3D ETAS model is about 1. What happened, which gave us a big difference. So this alpha value showing the difference of in trigger between the big event and small events. When alpha is big, it means most of aftershocks are triggered by a few events, of the biggest a few events. So this is one thing we should remember, the alpha value. And another thing is the likelihood. If we look at the likelihood model here, so we should see to compare the likelihood here. So we add, after we add a histogram distribution for the 2D ETAS model and finite source ETAS model, we found the likelihood, the first 3D is very high. For the 2D ETAS model, for the finite source, 2D ETAS model is the worst, and the finite source is in between. So what happened? Why the depth is so important? So this is the kind of depth and the against occurrence time for all of the events. So we can see the depth information is very abundant. The information in the catalog. So for the clusters, the cluster always around the parent, the main shocks. So the clustering in space is so evident, and this is why we have a great improvement in the depth. The 3D ETAS model have some good thing, but they have some problem. We will come to that problem later. But before that, we compare what happens with the declustering. So for the background, how many background events obtained by the 2D ETAS model, 3D ETAS model, and finite source ETAS model? They are similar. And also, what happened with the critical parameter, which is also named the branching ratio. So the branching ratio for the 3 model are also consistent. So that means with the three model to declass the catalog, the background seismicity will almost the same. So now we compare the background seismicity in different regions in this one, and this is the background events created by the different models: the 2D model in gray, 3D model in magenta, and the finite source in thin blue curve. But in fact, those three models are almost the same. And also, we can see the background. We assume the model is constant, but it's not constant in time. There is some changes related to some bigger scale. This is L'Aquila, Emilia, and the Nocha sequence. So, and for the finite source ETAS model, within the aftershock zone, the finite source ETAS model, this is region 4 is the Emilia aftershock zone. So the background is lower. But for the far region, the aftershock is a bit higher. The finite source ETAS model gave a higher background events, higher background range than the other model. So this is slightly different. And also we can see the background event is something like kind of before and after the major earthquakes. So we have some changing about the background seismicity. This is like this after the Emilia event. So we have a changing point around here, but it's not immediately. Someone consider those as some fluid transporting problem. So now we come to the problem of the three models. The most model we are going to divide the events into different family trees. So now we look at the number of direct offspring triggered by each of those 6 big events. So this is the number estimated from 3 models. So this figure is not difficult to read. This table is not difficult to read. I plotted it into figures. So this is the L'Aquila events. So this is a direct number of direct offspring. And those are the direct and indirect. That means all the descendants. So we can see the finite source model always gives the maximum number of direct offspring. 2D in average, something like that. But for 3D model, it's really terrible. That means the very few direct offspring here. So if we look at the direct number of offspring for each events against the time. So this is the 2D ETAS model, 3D ETAS model. This is direct offspring. This is the finite source ETAS model. We can see the finite source ETAS model gives the quite reasonable classification. Most of the aftershocks are produced by the major 6 major events. So, but for the 3D, what's wrong with the 3D ETAS model here? So this is because, sorry, not. So this is because of the effect of using the isotropic spatial response become more serious in 3D ETAS model. So if we look at this map, this figure, we can know much about that. So for most big events, their hypercenter is not in the middle of the cluster in the depth. It's just on the boundary of that. So for the ETAS model fitting, so it's more likely, okay, treated as a kind of isotropic triggering from one and then transfer from another and then to the end. So this is why the ETAS model, the 3D ETAS model, classifies the family tree in a way not so good. But because the depth information is so abundant, and the 3D ETAS model is the fits the seismicity the best. So another interesting result is to make comparison between the direct observable productivity and seismic slips. So those contour lines are co-seismic slip obtained by Italian researchers. And these colors here are the productivity density obtained by the finite source ETAS model. So this is for the Laclay events. We have these two parts as a part with maximum slip. So those two parts are with maximum direct aftershocks. And Emilia events, the first one, and the second Emilia event. So this one is those one a bit overlap, but this is for the amateur events. The part is around highest aftershock is around here, and this is the virtual event, and this is the notch event. So one of the conclusion is for the distribution of direct aftershocks, it's not always at the part of the the biggest slip area, but neighboring, always nearby, but very difficult for them to overlap. So this is a kind of short summary on the seismicity in Italy. So we can see the characteristic of seismicity varies in space and in time in the Italy region during those something like 12 years. And also in the rapid plane of the six strong shocks in Italy, the direct aftershocks tend to occur neighboring the part with the biggest slip on the rapid plane, but seldom overlapping, implying that the aftershock compensates the rapid of the main shock. The location of small events can be used for us to invert the focal rapid geometry. So with the productivity density function affect the focal rapid geometry. So, and also the finite source ETAS model we implemented that is a kind of to take incorporating the effect of full geometry of large aftershocks. So it corrects the problem caused by anisotropic response in the point source ETAS model, enhancing the triggering effect of the large events, which gave a very large alpha value, and also give more reasonable classification of family trees in kilowatt. For the 3D ETAS model, it operates the depth information and much improve the data fitting, but the effect of using isotropic spatial response kernel become more serious. And the third one, we hope a 3D plus finite source ETAS model is more plausible. We have done it already. We have done this research already. Now trying to get results published right now. And also the focal mechanism can be also included in the ETAS model. Aftershock have similar focal mechanism to the main shocks. So thank you. This is the main idea about the aftershock modeling. All the models are wrong, but some of them are useful.
Thank you for this very comprehensive lecture on ETAS. I think that, there are many aspects that have been touched during the presentation. Maybe there are questions either from basic notions or more recent.
This put too many contents in this very short talk, and also because this is a kind of to our talk, Antonella asked me to shrink it within something like 15 minutes.
Oh, we are not so strict with that.
Yeah.
A
bit rush.
Yeah. We have learned about new, let's say, ETAS model more, let's say, refined with new possibilities. So maybe you have questions or doubts or let's say, remarks on this new.
Yeah,
Okay, question. When you talk about finite source, how do you establish the shape and the of the finite source in the beginning?
Page up.
Because after you discretize this area.
So if you look at this one,
so in fact, I select very large region.
Um,
So after the iterative algorithm, so the productivity around the boundary becomes 0. So the initial selection of the aftershock zone, the finite source zone, is not very important. It will finally converge.
Is data-driven in some sense?
Pardon?
The finite source is data-driven.
Yes. So it's obtained by data-driven.
Okay. Thank you. Thank you for specifying. This is very important that you are not using prescribing before.
I go with a similar question. You showed us the results obtained in Italy using the EasyDay catalog that is quite a long catalog, and not only long catalog, but it has some problems of quality.
Yeah.
For example, the depth distribution that you showed us clearly fixed the point that most of the events are given at a predefined depth, the 10-kilometer depth that is given as a fixed solution. So
Yeah,
my question is, did you try to apply your algorithm to more precise catalog released after each main sequences? For example, the L'Aquila, Emilia, and the Central Italy sequence has their own catalog done with a better quality. Did you try to apply?
Not yet.
Not yet.
I hope to do that. So it's very pleasant. So those kind of people with the default depths is very extreme. So look here, it's 12. It's a first year, and they change 12 to 10 afterwards. So I think another depth is around 5 and 2. There's 3.
Level of starting
Default initial value for the depths.
So probably the bad results you obtain, but comparatively, the bad results you obtain with the 3D ETAS model are due to this imprecise definition of the depth, right? Not necessarily.
No, we didn't do it this time. But for the precise model, we should consider the probability the operator using the default depth for the depth.
And another question that is somehow related: what's the minimum size of the catalog you consider to be analyzed? I mean, for statistical reasons, you are not going to analyze a set of very few events. What's the threshold you suggest?
I suggest is the catalog should be relatively complete for most of the aftershock sequence in the catalog. So the smallest catalog I analysis is about something like 900 events. That's for the Taiwan catalog. The trouble, in fact, for the ETAS model is to model the behavior of the aftershock sequence. But most of the aftershock sequence have a short-term missing. It's basically for small events. So for the ETAS model, if we trying to fit the ETAS model to a catalog with
something earthquakes of small magnitude, sometimes it doesn't work well. So this is because the information we want to know are missing.
I wonder why you are focusing so much on finding fault and fault parameters, focal mechanisms, and you develop your aftershock guess on those two environments, let's say, instead of using the Coulomb stress that comes from the finite fault rupture. I think I would figure out that the stress propagation drives much more the aftershock distribution than the single patch of the fault, and that fault parameters are, for aftershocks, are much more difficult to estimate, to be estimated. So I guess that using Coulomb stress that you can easily, let's say, easily calculate after a main shock would be a much more effective way to drive the aftershock distribution.
Excellent idea. I completely agree with you about the importance of using Coulomb stress in the aftershock description. The trouble for us currently, there is several things. One is the Coulomb stress, the calculation of Coulomb stress. So in fact, it's for far field, it's quite good. But for the near field, because of the uncertainty of the fault shape, also the distribution of the fault, distribution of the slips, so the error for near field is huge. But aftershocks mainly in near field. This is one problem. Another problem is not problem. It's just another comment is during our talk about aftershock migration, directly within the cluster, the Coulomb stress should be considered in this way. But we are still working hard, trying to find a good solution. Seem to be something like a universal solution for such kind of modeling. Thank you very much.
Any other question? Okay. So I'd just like to thank you for this presentation, and also I would like to add that many persons here are involved in catalogs compilation, magnitude, homogenization, and so on. So I would like just to inform you that Jiancang is also working on some Bayesian approach for computing, for homogenizing magnitudes, not simply using regressions between different types of magnitudes, but also using more, let's say, educated approach for this kind of conversion and integration of different data sets into a single catalog. So if you are interested in this specific topic, this afternoon we are going to discuss in CRS in Udine, but also you may wish to contact me to learn about this possibility. So it's another field except ETAS that was.
We are working much more on data. We found the problem inside data itself is more difficult than the other.
Thank you. Thank you.
Thank you. Bye.
Oh, thank you very much. Thank you very much.